Now it's time to introduce the method of generalizing from generic particular. Now here are the suggested steps. Step 1. Express the statement to be proved in this form. So I mentioned earlier, rewrite that into conditional statements. If you're a if you are new to the world of proof, this is definitely a very good practice. What's the advantage of that? That means if you are able to convert this, you are very clear what's the P of X, which is the hypothesis or assumption or premise, right? So that it's very clear, and then you are very clear that what needs to be concluded or what needs to be proved. So that's what I would suggest. Do not skip this step when you are new to proof. Second, once you clearly rewrite the original statement into this form, if it is not in this form yet, rewrite that. Then you start the proof by assuming X to be arbitrarily chosen from this set D. So X is arbitrarily chosen element from set D. Why do we do that? Because this is for all, that means arbitrarily chosen from set D. At the same time, P of X is true because that's your assumption. So that's usually the language will be used. Suppose X is from this set D and this statement is true. That's what you would say. And then the next, you will have to use the method of logic, use the rules of logic, try to step by step reach to this conclusion, show Q of X is true by using definitions, previous established results, and rules of logic. Now, of course, this is the beginning. We'll prove something that's very fundamental. The focus is to make sure that you follow the whole flow of this flow chart. So focus on writing the correct step. A word of warning. So it is important that when you write any step, you need to be very fully ready to defend what you write. So just imagine that whenever you say something, your audience is gonna ask you, how is this true? Where is this from? Then you need to prepare to defend that statement. In other words, what you write need to support your conclusion. Okay, that's important. Always ask yourself, do I have enough reason to say this? All right, let's take a look at the first theorem that we want to prove. The sum of two even integers is even. Okay, do you see that this is not at all in this form? Okay, this universal conditional statement, this is not at all. So therefore, you really have to try your best to rewrite this into for all x, p of x, q of x, this form. Okay, let's try. It says choose the sum of two even integers. Well, I see now even integers, right? So therefore, this is a really good place for me to introduce variable. I'm going to call it as m and n. Okay, and then it says the sum of two. This two seems to be arbitrary. This two doesn't specifically say which two, so it's pretty generic. So therefore, this two will be arbitrary. This two will be like for all. That's how I feel like for all is needed. And it says integer. Okay, so here I'm gonna say for all m and n, I need two integers. They are both from integer. And now the sum is even, right? That's the sum is even. But of course, we still need to look at the sum of two even integers. Like m and m integers, they have to be even so that the sum is even. So I'm going to say if m and n are even, then the sum is even, right? the sum, which means m plus n, is even. This is always a good moment for you to go back and just read the theorem and then try to rewrite it. I would not be surprised if someone's, especially the students who are new to proof, that it will take quite a while or even take 10 minutes or 20 minutes or even an hour to rewrite a statement into, rewrite that into universal conditional statement. This is not a trivial step. This is pretty, sometimes can be tough. It takes time, it takes training for you to be proficient at that. Okay, so now we've got that done, and now let's start with the proof. Okay, this is just restatement of the original statement, just in symbolic form. So here's the starting point. We are going to say, suppose there are several different ways to say that. This is one popular way. Suppose m and n are integers and they are even. Okay, that means I combine these two together. Suppose m and n are even integers. Oftentimes this is also popular. Instead of using suppose, we can say let m and n be even integers. So they are equivalent, but they serve the same purpose. That's what you begin with. You assume that. Okay, so either way will be good. So I'm going to also say, or let m and n be even integers. Okay, and what do we want to show? So here's what we already done. We assume that m and n, they're even, they're integers, so that's what we have assumed. Then is the conclusion, right? So therefore, this is what we want to show. Then want to show m plus n is even. Okay. Now, oftentimes this is where I begin to ask my students to begin to think, always think about this way. Ask yourself, like, what does it take for you to make this conclusion? Like, what does it take for you to conclude that m plus n is even? That traces back to the definition of even. How can we show something is even? Isn't that in other words, we need to, our job is need to search or look for or find an integer k, right? Such that this m plus n is equal to 2 times the k. So this is what we are trying to find. Okay. Once you are able to find this, once you are able to find that, you can conclude that m plus n is even once you get to this point. So keep that in mind. So now here's the detail of the proof. Okay. Here's the detail of proof. Now we'll begin, because you already suppose m and n are even integers, therefore I can say because, 3 dots like that, that means because. This means because. Okay, because m and n are even, therefore m, because m is even, we must be able to find a integer r, okay, so that m is equal to 2r, right? So for some integer r, right? Integer r. And similarly, n is equal to 2 times s for some s, integer s. Okay. Sometimes people can write this in a shorter one. I think I should, but at the beginning I try to be, I err on more detail than less detail. So sometimes just say therefore m is 2r. So sometimes you can condense it. M is equal to 2r and n is equal to 2s for some rs integers rs. So sometimes you can shorten that into a shorter statement. Now again, you look at your, always keep an eye on your to show, okay, want to show. So you're looking at m plus n, right? So therefore I'm going to say, therefore what is m plus n? M plus n is equal to 2r plus 2s. Well, we are going to do substitution. That's one of the assumptions that we made earlier. So we can do substitution, which is 2 times r plus s, right? Now, do you see that? Do you see that? Remember, once we are able to find an integer so that m plus n equals twice that integer, then we can conclude that m plus n is even. Do you see that we actually now have that? M plus n is equal to twice of this integer. This integer is r plus s, right? So now, which is equal to 2k, where, what is your k? K is equal to r plus s. So you see that m plus n equals 2k, and where k is an integer, right? Therefore, m plus n is even, which is to be proved, right? Which is to be proved. Okay, this little square with field, like solid field square, or sometimes just a square, means this is the end of the proof. So now that's how I would do. So again, even though this problem is very simple, the focus is how to translate that into conditional statements, and then how to begin, what do you assume, and identify what is to be shown. And then sometimes it's a very good practice to keep in mind, ask yourself, what does it take for this conclusion to be true? And then you begin with your assumption, and then try to use definition and then other results to derive the result that you want to show.